welcome to G Fun Facts Online. Today, we're diving deep into a story of ambition, innovation, and catastrophic failure. On June 18, 2023, the world was gripped by the disappearance of the Titan submersible during its expedition to the wreck of the Titanic. The tragic outcome, a catastrophic implosion, claimed 5 lives and left behind a debris field of questions. How could a vessel designed for the most extreme environment on Earth fail so spectacularly? The answers aren't just in the ocean's depths, they're being revealed under the microscope through the fascinating discipline of forensic materials science. This is the story of how the very materials of the Titan are telling the tale of its own demise. To understand the failure, we first have to understand the submersible itself. The Titan was unlike almost any other deep-sea vessel. For decades, the gold standard for deep-diving pressure hulls has been a simple, robust design. A sphere made from a single, high-strength metal, usually titanium. A sphere is the perfect geometric shape to resist the uniform, crushing pressure of the deep ocean. It distributes that immense force evenly across its entire surface. But OceanGate, the company behind the Titan, and its late CEO Stockton Rush, took a radically different approach. They built the Titan around a cylinder, a shape that is inherently less stable under uniform external pressure than a sphere. But the most controversial choice was the material. Instead of a solid metal hull, the Titan's main body was a cylinder made from filament wound carbon fiber, a material famous for its use in the aerospace industry. This carbon fiber tube was capped at both ends with titanium hemispheres, bonded to the cylinder with titanium interface rings. The rationale was revolutionary, at least on paper. Carbon fiber has an incredible strength-to-weight ratio. Using it would make the Titan significantly lighter than an all-titanium sub, making it easier to transport and operate, and, theoretically, making deep-sea exploration more accessible and affordable. This was Stockton Rush's dream. The problem was, while carbon fiber is a miracle material for things like airplane wings, which experience pulling forces, or tension, its behavior under the immense compressive forces of the deep sea was largely unproven and not well understood. This experimental design choice was a major red flag for many experts in the submersible industry long before the fatal dive. Let's talk about the pressure. At the Titanic's depth, around 3,800 meters, or 12,500 feet, the water pressure is about 400 times greater than at the surface. That's a staggering 6,000 pounds pressing on every single square inch of the hull. Imagine the entire weight of a large commercial jet concentrated onto a space the size of a postage stamp. Under these conditions, any flaw, any weakness, any imperfection in the hull isn't just a problem, it's a death sentence. It leads to an implosion, a collapse so violent and instantaneous it's over in milliseconds, faster than the human brain can even process pain. The energy released is colossal. So the forensic investigation isn't about what happened in that final millisecond, but about the weeks, months, and even years of material degradation that led to it. The prime suspect from day one was the carbon fiber hull. Unlike metals like titanium, which will bend, warp, and deform under extreme stress, a property called ductility that can provide a warning of impending failure, carbon fiber is brittle. When it fails, it doesn't bend, it shatters, suddenly and completely. The recovery of the Titan's wreckage from the seabed was the crucial first step. The debris was found about 500 meters from the bow of the Titanic, in a relatively small, concentrated area. This pattern told investigators that the implosion likely happened at or near the submersible's maximum operating depth, where the pressure was greatest. The U.S. Coast Guard and the National Transportation Safety Board, or NTSB, began the painstaking process of analyzing every twisted and shattered piece. It's like an autopsy for a machine. And what they've found so far paints a damning picture. The Coast Guard's Marine Board of Investigation has already called the implosion a preventable tragedy. They concluded that the key factors were OceanGate's inadequate design, flawed certification process, and poor maintenance and inspection. The devil, as always, is in the details. One major finding reportedly points to a failure of the adhesive that was supposed to bond the carbon fiber hull to the titanium end caps. But the most revealing evidence comes from the carbon fiber itself. An NTSB engineer reported that the hull material showed clear signs of wrinkles, porosity, and voids that were present since the day it was manufactured. In a high-performance composite, these are not minor blemishes. They are critical defects. Imagine a tightly woven fabric. Now imagine that fabric has tiny gaps, bubbles, and folds in it. When you put that fabric under immense pressure, where do you think it's going to fail first? Right at those weak points. These voids and wrinkles act as stress concentrators, creating points where the immense force of the ocean can begin to tear the material apart from the inside. The manufacturing process itself has come under intense scrutiny. Creating a flawless carbon fiber cylinder of this size is incredibly difficult. It involves winding thousands of carbon fiber filaments, applying layers of pre-impregnated fabric, and then curing the whole thing under heat and pressure. If this process isn't perfect, you get exactly the kinds of flaws the NTSB found. Adding to the concern were reports that the carbon fiber used for the hull might have been expired stock purchased at a discount from Boeing. While Boeing denies any record of the sale, the very possibility that out-of-spec materials were used in a life support system for such an extreme environment is a terrifying prospect for investigators. Perhaps the most chilling piece of the puzzle is a warning that came more than a year before the disaster. During a dive in 2022, the Titan's own onboard acoustic monitoring system, a system designed to listen for sounds of hull stress, recorded a loud acoustic event, or a bang. At the time, it was explained away. But materials scientists now almost universally agree on what that sound was: the carbon fiber delaminating. This means the layers of the composite material were beginning to separate and break under the strain. This wasn't a subtle hint. It was a blaring alarm bell signaling that the hull's structural integrity had been fundamentally compromised. The hull was actively failing, dive after dive. This single event should have been enough to permanently retire the vessel. The fact that it continued to dive is central to this tragedy. This leads us to the biggest issue of all: a complete and deliberate disregard for established safety protocols. OceanGate intentionally chose not to have the Titan certified by a recognized classification society like the American Bureau of Shipping. These are independent bodies that have spent decades developing rigorous standards for building safe marine vessels. Stockton Rush publicly argued that the certification process was too slow and expensive, and that it stifled the kind of innovation he was trying to achieve. But certification isn't just red tape. It's a thorough, independent review of a vessel's design, its materials, its construction methods, and its testing. A certified sub would have its materials tested for their properties. The finished hull would undergo non-destructive tests, like ultrasonic scans and X-rays, to find those exact kinds of hidden voids and flaws that the Titan's hull contained. By sidestepping this entire process, OceanGate became the sole arbiter of its own safety, a decision that proved fatal. Sadly, the Titan implosion is not without historical precedent. The world of deep-sea exploration learned many of its hardest lessons from military submarine disasters. The loss of the U.S. Navy submarine USS Thresher in 1963, which killed all 129 men aboard, was a watershed moment. The investigation revealed that the sinking was likely caused by a failure in a single silver-brazed piping joint. A tiny component failure led to catastrophic flooding. In response, the Navy created the SubSafe program, an incredibly rigorous quality control and certification process that covers every single component of a submarine's hull and critical systems. SubSafe is built on the philosophy that you must assume failure is possible and engineer systems with redundancy and intense quality control to prevent it. It's the polar opposite of the philosophy that guided the Titan's development. The Thresher investigation proved the absolute necessity of material quality, fabrication techniques, and independent oversight, lessons that echo powerfully today. The investigation into the Titan is still ongoing, and the final reports will likely provide even more granular detail about the precise sequence of material failure. But the legacy of this tragedy is already taking shape. It has exposed a significant regulatory loophole that allowed a private, experimental, and uncertified submersible to carry paying passengers into one of the most dangerous environments on the planet. We can expect to see a major international push for stricter regulations and mandatory certification for all deep-sea tourist vessels. The Titan disaster serves as a brutal reminder that the deep ocean is an unforgiving frontier. It doesn't care about innovation or cutting-edge materials if the fundamental principles of engineering and safety are ignored. The silent, shattered fragments of the Titan, now laid out in a laboratory, are telling a story. It's a story of preventable failure, of warnings ignored, and of the catastrophic price of hubris. And for the future of deep-sea exploration, it's a story the world must listen to.